Let's get started with a high-level overview of Apache Spark and what it's all about, what it's good for, how it works. Let's dive in. Let me give you a brief high-level overview of what Apache Spark is all about. So a little introduction of the whole concept. So what is Spark? Well, if you go to the Spark website, they give you a very high-level hand-wavy answer, a fast and general engine for large-scale data processing. It slices, it dices, it does your laundry. Well, not really. But it is a framework for writing jobs or scripts that can process very large amounts of data, and it manages distributing that processing across a cluster of computing for you. So basically, Spark works by letting you load your data into these large objects called resilient distributed data stores, RDDs, and it can automatically perform operations that transform and create actions based on those RDDs, which you can think of as like large data frames, basically. And the beauty of it is that Spark will automatically and optimally spread that processing out amongst an entire cluster of computers if you have one available. So no longer are you restricted to what you can do on a single machine or a single machine's memory. You can actually spread that out to all of the processing capabilities and memory that's available to a cluster of machines. And in this day and age, computing is pretty cheap. You can actually rent time on a cluster through things like Amazon's Elastic MapReduce service, and just rent some time on a whole cluster of computers for just a few dollars and run your job that you couldn't run on your own desktop. So how is it scalable? Well, let's get a little bit more specific here on how it all works. So the way it works is you write a driver program. It's just a little script that looks just like any other Python script, really, and it uses the Spark library to actually write your script with. And within that library, you define what's called a Spark context, which is sort of the root object that you work within when you're developing in Spark. And from there, the Spark framework kind of takes over and distributes things for you. So if you're running in standalone mode on your own computer, like we're going to be doing in these upcoming lectures, it all just stays there on your computer, obviously. But if you are running on a cluster manager, Spark can figure that out and automatically take advantage of it. Spark actually has its own built-in cluster manager, so you can actually use it on its own without even having Hadoop installed. But if you do have a Hadoop cluster available to you, it can use that as well. So Hadoop is more than MapReduce. There's actually a component of Hadoop called Yarn that is just separating out the entire cluster management piece of Hadoop. And Spark can interface with Yarn to actually use that to distribute optimally the components of your processing amongst the resources available to that Hadoop cluster. And so within a cluster, you might have individual executor tasks that are running, and these might be running on different computers. They might be running on different cores of the same computer. And they each have their own individual cache and their own individual tasks that they run. And the driver program, the Spark context, and the cluster manager work together to coordinate all this effort and return a final result back to you. The beauty of it is all you have to do is write this little script here that uses a Spark context to describe at a high level the processing you want to do on this data. And Spark, working together with the cluster manager that you're using, figures out how to spread that out and distribute it. So you don't have to worry about all those details. Well, until it doesn't work, obviously, you might have to do some troubleshooting to figure out if you have enough resources available for the task at hand. But in theory, it's all just magic. Now, what's the big deal about Spark? I mean, there are similar technologies like MapReduce that have been around longer. Spark is fast, though. And on the website, they claim that Spark is up to 100 times faster than MapReduce when running a job in memory, or 10 times faster on disk. Of course, the key words here are up to. Your mileage may vary. I don't think I've ever seen anything actually run that much faster than MapReduce, and some well-crafted MapReduce code can actually still be pretty darn efficient. But I will say that Spark does make a lot of common operations easier. MapReduce forces you to really break things down into mappers and reducers, whereas Spark is a little bit higher level, so you don't have to always put as much thought into doing the right thing with Spark. And part of that leads to another reason why Spark is so fast. It has a DAG engine, a directed acyclic graph. That's hard to say. A directed acyclic graph. Say that 10 times fast. And wow, that's another fancy word. What does it mean? What it means is that the way Spark works is you write a script that describes how to process your data. And you might have an RDD that's basically like a data frame, and you might do some sort of transformation on it or some sort of action on it. But nothing actually happens until you actually perform an action on that data. So what happens at that point is Spark will say, okay, so this is the end result you want on this data. what are all the other things I had to do to get up to this point, and what's the optimal way to lay out the strategy for getting to that point. So under the hood, it will figure out the best way to split up that processing and distribute that information to get the end result that you're looking for. So the key insight here is that Spark waits until you tell it to actually produce a result. And only at that point does it actually go out and figure out how to produce that result. So it's kind of a cool concept there, and that's the key to a lot of its efficiency. Spark, very hot technology, relatively young, so it's still very much emerging and changing quickly. But a lot of big people are using it. So Amazon, for example, has claimed they're using it. eBay, NASA's Jet Propulsion Laboratory, Groupon, TripAdvisor, Yahoo, and many, many others. I'm sure there's a lot using it that don't fess up to it. But if you go to the Spark Apache wiki page here, there's actually a list you can look of known big companies that are using Spark to solve real-world data problems. So if you are worried that you're getting into the bleeding edge here, fear not. You're in very good company with some very big people that are using Spark in production for solving real problems. And it is pretty stable stuff at this point. It's also not that hard. You have your choice of programming in Python, Java, or Scala. And they're all built around the same concept that I just described earlier, the Resilient Distributed Dataset, RDD for short. And we'll talk about that in a lot more detail in the coming lectures. Spark actually has many different components that it's built up of. So there is a Spark core that lets you do a lot. You can do pretty much anything you can dream up just using Spark core functions alone. I mean, I have a course where I make an entire recommender system just using Spark core, but there are these other things built on top of Spark that are also useful. For example, Spark Streaming is a library that lets you actually process data in real time. So data can be flowing into a server continuously, say from weblogs, and Spark Streaming can help you process that data in real time as you go forever. Spark SQL lets you actually treat data as a SQL database and actually issue SQL queries on it, which is kind of cool if you're familiar with SQL already. MLLib is what we're going to be focusing on in this section. So that is actually a machine learning library that lets you perform common machine learning algorithms with Spark underneath the hood to actually distribute that processing across a cluster. So you can perform machine learning on much larger data sets than you could have otherwise. And finally, GraphX. That's not for making, pretty charts and graphs. That refers to graph in the, network theory sense. So think about a social network, for example. That's an example of a graph. And GraphX just has a few functions that let you analyze the properties of a graph of information. Now, I do get some flack sometimes about using Python when I'm teaching people about Apache Spark, but there's a method to my madness. Now, it is true that a lot of people use Scala when they're writing Spark code because that's what Spark is developed in natively. So you are incurring a little bit of overhead by forcing Spark to translate your Python code into Scala and then into, Java interpreter commands at the end of the day. But Python's a lot easier. And you don't need to compile things. Managing dependencies is a lot easier, so you can really focus your time on the algorithms and what you're doing and less so on the minutia of actually getting it built and running and compiling and all that nonsense. Plus, obviously, this course has been focused on Python so far, and it makes sense to keep using what we've learned and stick with Python throughout these lectures. However, I will say that if you were to do some Spark programming in the real world, there's a good chance people are using Scala. However, don't worry about it too much because in Spark, Python and Scala code ends up looking very similar because it's all around the same RDD concept. The syntax is very slightly different, but it's not that different. So, if you can figure out how to do Spark using Python, learning how to use it in Scala isn't that big of a leap, really. So let's go look at some examples and dive in. So that's the basic concepts of Spark itself and why it's such a big deal and how it's so powerful in letting you run machine learning algorithms on very large data sets, or any algorithm really. So let's talk in a little bit more detail about how it does that and the Resilient Distributed Data Store next.